Hello and welcome to the next unit or lesson, in the exponential unit. So we're going to start to look at graphing exponential functions, how they change depending on the value of b. So let's first get started. Just a little bit of opening question stuff about the weird powers, negative exponents, and that we've seen recently. So here's some example questions. If you needed some help with the previous assignment, this should help a bit. So one of the things sometimes you get asked is just to write as single powers. And so using our rule that we know that a to the negative n equals 1 over a to the positive n, then we can just switch this form here to a 1 over 3 to the positive 2, right? And we weren't even asked to evaluate. If you were asked to evaluate, right? If we were asked to evaluate, then you'd be like, well, 1 over 3 times 3, which is just 1 over 9. Right? A lot of people mistake this, and we can make a note of this here. A lot of people mistake this for 3 times 2. Let's just point out that this is not 3 times 2. I'll go with a different color for emphasis here. So just note that this is not 3 times 2 equals 6. If it was, it'd be kind of redundant, right? Because 3 times 2 looks like this versus 3 to the power of 2. Why would we bother having a different version, right? So it's not 3 times 2, it's 3 times 3, right? And then it's just 3 on itself twice, right? So if we go here, it's twice. That's what the 2 means in that case. Hopefully that's already obvious, but I know it's a common mistake that I see in students, so hopefully that helps. All right, so next one here, if we were doing this one, we could right away make this part be positive, right? If that's our goal. And so we have 1 over that bracket to the positive 3. And so that's going to give us an x squared, y to the negative 3 still in here, like that. And then the other rule that we can apply that we know is that a to the n all to the power of m equals a to the n times m. And it goes on to each piece. So we have a 3 under there and a 3 under there. So that gives us 1 over x to the power of a 2 times a 3 and y to the power of a negative 3 times a 3. So that's going to give us a 1 over x to the 6 and a y to the negative 9. And let's get here. I'm just going to pause for a sec. I want to modify things. I don't want you to wait around for that. Just give me a sec. All right, here we go. So I just moved the stuff to the other page. So there's another way we could go about this as well here, but what we have here is the 1 over x to the 6. And then we know this one here can be written as 1 over y to the positive 9. So I probably should just ungroup that and make that look a little bit more like an exponent here. Group that. So I'll show you another way to deal with this one, but a fraction rule is that we know is to divide by a fraction. So let's say to divide by a over b, you instead multiply by b over a. It's invert and multiply. And so we can do that. We can say, okay, well, this is then 1 over x to the 6 times y to the 9 over a 1. We've inverted and multiplied. And so we end up with y to the 9 over x to the 6, which is a little bit of a weird process for sure. So another way, a little bit of an easier way, just noticed here that this might have been nicer, is if we had of, let me do that up top actually. If we had of multiplied this thing on first, like that, we would have ended up with x to the 2 times the negative 3 and y to the negative 3 times the negative 3. And so it would have given us x to the negative 6, y to the positive 9 in the first place. So we wouldn't have had that negative in the bottom. So then we just switch this one to be a 1 over x to a positive 6 times a y to the 9, which gives the result. that we ended up with eventually. The other method gives us the y to the 9 over x to the 6. If you can do something more than one way, or with a different sequence of steps, kind of builds confidence that it's correct, right? If you get the same answer multiple ways, must be doing something right. The zero exponent stuff comes up here. Really, that's 49. Numerically, you can say, well, that's 49 divided by 49, right? So 7 squared is 49, so it's 49 over 49, which clearly is equal to 1. If we do our analysis fully with exponents, we would say that's a 7 to a 2 take away 2, which is a 7 to a 0, which we defined, or we determined, I should say, we realized yesterday by looking at number logic is equal to a 1, right? So I'm just going to make that be sort of a obvious 1 rather than just a line like I normally would. Kind of emphasis, right? Emphasize that it's a 1 for sure. And then here, what would we have? Well, we'd have the 3, and the x wouldn't really change at all. Then we'd just have the y to the 2 take away 2. So 3 over x, 3 y to the 0, I guess, over x. And so we'd have 3 times 1 over x. And so it's just 3 over x. Just to remind you of, there's new things that we looked at. I didn't do any examples of the root fraction exponent stuff. If you need any help with that, let me know as well. I can post some more help with that. All right, so the graphing stuff that we said we're going to get going on here. The most basic form is when an a equals 1. So I might do that as well in this lesson. So what if you have 1 to the x? It does say when it's greater than 1 in there. Set a, not, yeah. So when b is greater than 1. But we can look at the 1 example as, actually, let's not do that. Let's just look at these examples and see how it goes, all right? So I'm just off track myself with my thoughts here. So the a is if we have a 1 in front of here, not the power. That was silly for me to do that because obviously had 1 to the power of x would always just be 1, right? And so it wouldn't give an exponential situation. So if b was 1, why are we greater than 1? Because if b was equal to 1, it wouldn't be exponential. It would just be 1s. It'd be just a flat straight line. So we will use graphing tech to just take a peek at these and see what they look like. So follow along here, do this kind of thing. Make sure to be able to do this kind of thing yourself as well. So let's go to a new tab over here, and let's type in either GeoGebra or Desmos or whatever graphing program you're comfortable with. I like GeoGebra and Desmos really. So GeoGebra graphing calculator. And so if I typed in 2 to the power of x, so 2, and then has this feature here for power of, or you can use see it here. So I had to use that one, but there's a little upside down V, it's shift 6, that'll work too. Anyway, so there you go, that's 2 to the power of x, so we see it on the graph. And then let's do another one. Let's do the 3 to the power of x, like it said, right? 2, 3, and 4, all to the power of x. So if we had a 3 to the power of x, so I'll do the other version of things here. Shift 6x and 4, shift 6x. So those are all of the graphs that we want to sort of get to know, and so let's just show the first one so we can look at it. Clearly it goes through 1. And then if we were to pick out some values that might be easy, we notice at 1, it's at 2. So 1, 0, 1, 1, 2, and then let's go 2, 4. Okay, so we can graph those pretty easily. Let's go back here and show that. So 0 was at 1. So let's do this one, I believe. So 0 was at 1. And 2 was at 2. 2 is at 4. Obviously, we're just doing 2 to the power of 2, so 2 squared. 2 to the power of 1 is just 2. 2 to the power of 0 is 1. That's kind of why we need to do that, right? So if you're doing a table of values for this, x and y equals 2 to the x, our table of values would have been, negatives as well, of course. So that's why we didn't analyze all this stuff. But so -2, -1, 0, 1, 2, 3, and so on. So this would be 2 to the power of 0, which we know is 1. This would be 2 to the power of 1, which is just 1. 2 to the power of 2 means 2 squared. So it's 4, and so on. 2 to the power of -1, we just learned yesterday that means 1 over 2 to the power of 1, which means 1 over 2, which means 0.5. So it should be pretty obvious where these numbers are coming from. We're going to do another day of this tomorrow where we're punching in numbers and graphing and so on. But for now, it's mostly just supposed to just be about the pictures, just to get you used to what they look like. But this would be 2 to the -2, which is 1 over 2 to the 2, which is 1 over 4, which is 0.25. And which we'd see from the graph as well. But instead of having to bounce back and forth, let's just do it here. So we got our half, then we got our quarter. It's a little hard to, But yeah, so there's our exponential shape, like this, like this. And so you'll find in the calculator that it never gets to 0. So if you did 2 to the power of -10 or something, it'd still be 0 decimal something, right? So I'm trying to show 0, skimming along the 0, and yeah. That. There we go. I like that. All right, so that's your y equals 2 to the x. And if we think about the numbers here, 3 to the power of 1. So let's go here. 3 to the power of 0 would still be 1. 3 to the power of 1 would be 3. 3 to the power of 2 would be 9. 3 squared is 9, right? And then on the other end, 3 to the power of, let's go to the graph here. 3 to the power of, let's add this one onto it. See how 3 to the power of -1 is smaller? It's 1 over 3 now, right? So it's 1 over 3. So it's 0.333 if you look at the number across the screen here. It's at 0.333. So we'll have this one go below here. So it's again, it's really hard to show this, but we can show it taller on this end for sure, and going below down here and over, skimming along 0. And then the 4 to the power of x is easy to analyze as well. We can see it on here first, of course, if we want. So if we're comparing the 4 one, see how at 4 to the power of 1 is 4. 4 to the power of 0 is still 1. Anything to the power of 0 is 1, and so on and so on. Right? 4 to the power of -1 means 1 over 4. So this number right in here where my mouse is flashing sort of there is 0.25. Yeah, -1 or at 0.25. So let's do that. So we'd have the red one, we'd be at 4 and a 1. And so it's going to be even steeper like this, and it's going to even go below the other one and over, like that. Not the right curvature there slightly, but you get the idea. Okay, so if we're comparing the graphs and we're saying like, how are they similar? How are they different? Well, similar, they all go through 0, 1. So they're all through the same y-intercept, 0, 1. They all have a slow section and a fast section going left to right, right? So they have they all have this pattern here of like this, where it's slow increase to fast increase, going left to right. Just rather than trying to give words, I just use the picture. How are they different? So how are they different? Let's do, are they different? Well, they're different because the bigger the b value, the larger b value, means they increase quicker and decrease quicker. So increase and decrease quicker. Right? The power of 4 one went to 4 after 1 step. The other one only went up to 2 and so on. Yeah, that's right. The 16, the red one would have gone to 16. So I was just sort of thinking about numbers in my head. So this one would be at 2, right? At x equals 2, this would be at 16. Right? Because we'd have 4 to the power of 2 would be 16. So it would be way up at 16. The graphs have one point in common. I guess we already pointed that out. It's this 0, 1 point. Do any of the graphs intersect the x-axis? No, they don't. And so that's really what we're trying to do, is we're just trying to analyze the graphs and look at them and see how they look using technology. Technology is a little bit better at zooming in and so on to show this stuff. So what I'll do, since my diagrams, I wouldn't classify them as the best ever, let's copy this in there. So I'm going to copy the names or what the graphs are in as well. And the pictures. That's pretty good there. Here we go. So pictures left something to be desired on the previous page, so it's looked a lot better. Okay, so the next one here, graphing. Yeah, there we go. So graphing, if the b value is between 0 and 1. So let's do 1/2 to the power of x. Let's just unshow, delete those ones or whatever, hide them or whatever. And I'm just going to put a bracket around the 2. Other side of the 2 here, a bracket and a bracket. And in here, I'm going to do a 1 divided by 2. Oops, it's giving me trouble here. There we go. Delete that. So the 1/2 x. And so let's look at what that looks like. Oh, it finally graphed on its own. I had to hit enter still or whatever, but that's what we get for that one. And so we can just draw it. Notice that it still goes through 0, 1. Zoom in a little bit more, and it tapers off backwards. Notice at -1, we're at 2. And at -2, we're at 4. So it's really the same graph as last time, only flipped in the XY direction, which is kind of neat. So let's draw that one. Again, we'll go blue. And so at 0, we have the 1. At this, it's going to be the 1/2 and so on. We said this was at 2 and 4. Right? Right. So the exponential graph, like that kind of thing. So there's our 1/2 to the power of x. And then we'll do the green one next. 1/3 to the power of x. Here we go. We'll change this one to be 1/3. I could just put in 0.333, but that's just going to be an approximation. So let's do 1 divided by 3 again. And enter. Enter. Oh, actually, I just have to hit the graph it. That's right. So we get that green one. See how it is? It's increasing. Sorry, the blue one, I should say, is increasing faster, just like last time. And then finally, the red one. I was messed up by my colors because my color choice on my lesson didn't match the GeoGebra color choices, unfortunately. What can you do? So the red is the fastest yet, right? So the 1/4 is the fastest one yet, just like the 4 was the fastest one yet. Just it's a decreasing situation. So we're going to do the same things here. So we've got the 1/3 one. When we do power of 0, you get a 1. When you do power of -1, you get the 3. Power of -2, it's 1 over the 3 squared, so 1 over the 9, right? So we get like that. And then this one, again, power of 0 is still going to be 1. And the power of 1 is going to be the 4. And then it goes up to 16 somewhere up here when it's 1, right? So let's just make that be tall and skinny and exponential shape. Underneath, barely and skims the 0. Right, so I feel like I want to just move this grid down just the hair. That looks better. So you can see they're above 0. And I'll do the same thing. I'll put the picture on the other page, on the next page as well. It's a more accurate version of things. So let's do that. And equations. All right. So what do we notice on these ones? Pretty similar observations. How are they similar? How are they different? Do they have one point in common? Like, yes, they have a point in common. It's the y-intercept here. The y-intercept is equal to 0, 1 for all. And that's, we should have said it on the other page too, but it's good to get it over here since any number, the power of 0 equals 1. That's our new stuff, just to make that connection back. Similar and different, well, they're all this kind of a shape, right? So they're all really a decreasing kind of shape like this. So I should put a grid here, I suppose, like that, like this kind of thing, right? They're all a decreasing shape, like that kind of thing. So they all have a fast section, a slow section of decrease. And do the intersect the x-axis? Like, no, they do not, right? Why don't they intersect that x-axis? Why do you think that is? Think about it a little bit or whatever, but basically, if you look at this case, we have 1 over larger and larger numbers, and for any particular number really, you just go to a really large number, it just becomes 1 over a really large, like an even larger number. So let's say 1 over an even larger number by having put it to the power of a large number, much larger number down here. If I could write the word larger, that'd be better, right? But that's really just going to give you 0.0000000, right? Never really 0. It's just going to approach 0. So some cases, the things you model don't really do that, like the coin flipping example. When we remove the coins, obviously we got to 0 coins, right? If you're doing a regression in Excel, it won't let you do, I found this out with a student showed me yesterday, they're looking for help. It wouldn't allow them to do an exponential regression because after the 6th trial, we had 0. So we changed it to 0.000000001, and then it was like, oh, okay, I can do that one. It literally wouldn't do an exponential regression because one of the numbers in the list was impossible for an exponential. But like I said, the math model doesn't really work for coins because they go to 0, where it does work really well for something like the wine barrel, where there's always, say, 10 milliliters of wine left, and a portion of those billions of molecules are the original one. And that just gets a smaller and smaller number. But in large quantity things like electrons and where there's bazillions of things, say getting half each time or a third each time, technically never go to 0. So, as the math model shows, weird stuff. So the summary of this, we have the graphs of b to the x when it's greater than 1 and less than between 0 and 1. We know that we have what we just did on the previous page, right? So for greater than 1, we've got this kind of a graph, and for between 0 and 1, we've got this kind of graph. So I'll put axes on there so they look more like graphs, but we have this kind of thing and this kind of thing. What happens if b is 1? Well, like I said, by accident there at the beginning, I was trying to do that, right? So if b equals 1, we'd have 1 to the power of x, right? And so regardless, this would always equal 1. So it doesn't give you an exponential. Like the graph would just be 1 the whole time, or whatever the number in front of that was. So it would just be at, in this case, 1. So it would just be like this. So this is like y equals 1 to the 1. Just be at 1 the whole time. So this is the same summary of this stuff, right? This one right here, up to the right, and so on. So that is summary of that stuff. Should be pretty straightforward from what we saw. So if you're graphing this by making a table of values, we'll just go ahead and do this, I guess. This is kind of getting into tomorrow's lesson stuff, but there's more practice tomorrow. This would be obviously 2 to the power of a -3, which if you evaluate with your calculator, just get an answer, right? But it's kind of nice to know that this equals 1 over 2 to the 3, which means 1 over 8. So if you didn't have like an exponent button or couldn't do negative exponents and so on, you could still do this. You'd just be like, oh, so it's 1 divided by 8, right? So 1 divided by 8. Oops, that's not what I wanted. Figure that. 1 divided by 8 is that's 0.125. And then 2 to the power of -2, similarly, equals 1 over 2 squared, which is 1 over 4, which is 0.25. 2 to the power of -1 is 1 over 2 to the 1, which is 1 over 2, which is 0.5. 2 to the power of 0 equals a 1. 2 to the power of 1 equals just 2. 2 to the power of 2 equals 2 times 2, which is 4. And 2 to the power of 3 gives us 2 times 2 times 2. I'm just showing extra steps here, but you obviously don't need to necessarily do all that. Now, the numbers we have, let's watch our numbers here for the pattern. We've got the 0.25, 125, the 0.25, that, just so we analyze the numbers because they're kind of all over the place. The number pattern here, if we notice, it's exponential, right? We're saying we know it's exponential, and so we'd be expecting a common multiple. So let's just check that. Otherwise, you might have been just randomly looking at first differences and second differences and so on. But if we look at the common multiple, if we do 0.25 divided by 0.125, what do we get? So 0.25 divided by 0.125, and we get a 2. So the common multiple was 2. How many times is a quarter go into a half? Twice. How many times is 0.5 go into 1? Twice. 1 goes into 2? Twice. 2 goes into 4? Twice. And 4 goes into 8? Twice. They're all 2s. Okay, so we have a common multiple of 2. Well, obviously here you may notice the common multiple is equal to 2. And if you make the connection to that equation, of course, we've got the common multiple of the 2. And we've got the equation that had, of course, a 2 in it, right? So there's your common multiple, of course, that we're multiplying over and over again. It's literally what it means, right? 2 times 2 once, then times 2 twice, and then times 2, and so on, okay? So if it's exponential, all I was doing here is if it's exponential, of course, you've got a common multiple. So if we go ahead and graph that, we'd have I kind of like to start at the 0 because it's so easy. You got 0, 1, then you've got your 1, 2, and your 2, 4, and so on. And we've already graphed this one, but this was, we know a little bit more about it now. We got a half, and then 0.25, and then 0.125, and so on. So this would just be skimming the 0 for quite a while in the slow section, and then going faster and faster. Okay, so I should have made sure to make that go through 8. So it should have gone through right there. That's all. Yeah, Okay, so that's the idea for that one. And then this one's extremely similar, obviously. So anything to the power of 0, 1/2 to the power of 0, anything's just a 1. 1/2 to the power of 1 is just 1/2 if you did it. On a calculator would certainly show that. 1/2 to the power of 2. 1/2 to the power of 2 means, of course, 1/2 times 1/2, which gives us 1/4, which is 0.25. 1/2 to the power of 3, again, is 3 of those things, so it gives us a 1/8, which is that 0.125 number again, and so on. So this is where our knowledge about the negatives comes into play here, of course, where we know this is 1/1/2 to the 1, which means it's just 1/1/2, which means we invert and multiply. So this is going to be equal to the 1 times the 2/1. Right? The flipped version here. I'll do it in green just to show what I did. So that gives us a 2, and so on. So this one is 1/2 to the power of -2, which is 1/1/2 to the 2, which is 1/1/4, which is 4/1 times that. So it gives us a 4 answer. And then this one, if we do the same process, we know that it's going to give 2 to the power 3 to the power 2 to the power 3. Sorry, so it's going to give 8. Skip the last one because didn't really have room here. I didn't think so. We have 0.25, 125, the 0.25, the 5, the 1, the 2, the 4, the 8, and of course we got the same idea. The common multiples. You're going to see that it's times 2 each time this way, right? Or actually, it shouldn't work backwards like that. Of course, it's divide by 2. Jeez. Right, so this is times a 1/2, right? The 4 over the 8, second divided by first. 4/8 equals 1/2. So we have this multiple of a half. Multiple of a half. All the way along. We have a common multiple of a half. Which again, we can make that connection back and say, oh, okay, of course we have a common multiple of a half because the number that's in here that we're multiplying by x times all the time is a half. So again, common multiple, it's exponential. Okay. So that is it for that. If you have any questions, let me know. And yeah, thanks for watching. Like and subscribe, as they always say, whatever.